Okay, so this talk is about the Earth moon resistance and nearest neighbor search, but really I wanted to maybe focus on one aspect and give you one thing that I find interesting is this connection between the Earth moon resistance and how we use probabilistic tree embeddings. So if you're familiar with probabilistic tree embeddings in approximation algorithms, this is kind of going to be a very similar context with one important twist. And a lot of the improvements will come from really focusing on that twist. Okay, and yeah, then we'll talk about this notion of data-dependent probabilistic trees. This is a notion that we worked on a few years ago, and they were really suited for the Earth mover distance, but there was one way in which they were suited for only one Earth mover distance computation. And in nearest neighbor search, you really want to compute many Earth mover distance computations because you're trying to find the closest point. So we'll see like a new lemma about controlling what happens to distortion on these trees. But I'll get into what all these different notions are. Okay, so let's get started. And I'm just going to define what the Earth mover resistance is. This is the metric space, but the Earth mover resistance is a metric defined over some ground metric. So the first things first, our underlying ground metric is always going to be RD with L1. And then the Earth mover distance is a metric over subsets of RDL1. Okay? So in particular, the inputs or the points, when I talk about points, I'm really talking about multisets, A and B, so A1 through AS, these are vectors in RD. And then the Earth mover distance between the point A and B, both of which are subsets, is the minimum over all bijections, so any way to match the points in A to the point in B, so as to minimize the sum of the L1 distance in the underlying ground metric, which was L1. Okay. So the point is to minimize overall possible bijections. This gives you a way to sort of transfer the Earth from A into the hole in B. Okay. And really, if you're familiar with like graphs, or you like to think about graphs, this is just the geometric version of the min-cost perfect bipartite matching, bipartite because we have the set A and B, where the underlying costs in the edges have this triangle inequality. In particular, they're the L1 distance between the underlying vectors. Okay, and we're going to be talking about approximate nearest neighbor search over the Earth mover distance. So let me just tell you what the picture looks like. Here we're getting to pre-process an entire data set of points. And remember, each point is a subset. And we want to arrange these into a data structure such that in the future, we can find the approximate nearest point, or approximate nearest subset, in my data set. Okay, so in this example, I have a data set of size 3, A, B, and C, and each one of my points is really a subset of 4 elements in the corresponding metric. Okay, so we have the squares, the circles, and the triangles, A, B, and C. And now you get those to pre-process. You build your data structure. In the future, I'm going to come with a query that is itself a set. These are the stars, and you haven't seen the query before. And the goal is to find, well, which one of my data set points was the closest, where the underlying distance itself has to go through this perfect match, the min-cost perfect match. Okay. By the way, if there's any questions throughout, just feel free to stop me. Okay. Is the problem kind of the definition clear? It's really the same context that Sasha was talking about this morning, where the underlying metric is this EMD. Okay. Cool.
Excuse me,
yes?
why you didn't use any of the set A or B in the, you don't use the set of A or B in the minimization, or is it just the?
Yeah, so this picture is supposed to say that, well, at the beginning you had the square, circles, and triangles, A, B, and C, that's all you had. You built your data structure, and now I came to you with a new query, so it's the stars, and this picture is supposed to represent that, well, the true nearest point, which in this case is a subset, would be, well, I take the stars and I compute the EMD to each of A, B, and C, and then I pick the smallest one. That would be the true nearest neighbor. That's a value that we're trying to output. Any other questions? Okay, so in this talk, all the guarantees are in terms of the parameter n, which is going to be the size of my data set, and the parameter s, which is going to be the size of the subset that I consider when I talk about EMD. Okay? So just to set notation and do a little bit of housekeeping, I'm going to refer to the EMD metric, this EMD s x dx, as the metric consisting of size s subsets of x. And really, there's two important parameters here. It's n, the size of the data set, which you could think of as being very, very big, and s, which is the size of the subset, or the representation of a point in the metric space consists of s points in Rd. Okay. Now, in your mind, you should think of n as being significantly larger than s, so that's a thing that we're trying to be sublinear with respect to. We don't want to scan through the entire data set. And s is still going to be a large parameter, but maybe think about it as 100 or 200. Okay. Cool. Oftentimes, the underlying ground metric, and like I said at the beginning, the one that we care about is Rd with L1. But as we'll see, this notion of probabilistic tree embeddings, it'll be very useful to change the underlying metric x. And instead of make it Rd, make it that a tree. And then finally, it turns out that for this specific problem of nearest neighbor search, it suffices to think about the underlying dimensionality d, as well as the aspect ratio delta, as some polynomial in S. So really now everything here depends on n and s. Okay. Cool. Okay, let me tell you about the prior work and then our main result. So the short story is that this metric space, this earth move resistance, is significantly harder than, say, the L1 or the L2 distance, and that's reflected on the approximation that we can achieve for efficient nearest neighbor search data structures. Okay, so back in 2004, Peter Indig gave a data structure such that for any epsilon, you can solve this problem with approximation, which is d log s over epsilon, with having space and preprocessing time essentially polynomial in the representation of the point, which is s times d, times n to the 1 plus epsilon, so minor polynomial overhead in the space and preprocessing time, but very fast query time. Okay, so the query time essentially looks at each point, there's n to the epsilon many times you need to look at each point. Okay, so this is, for epsilon being 0.1, this is very highly sublinear, but getting approximation, which is d log s. A few years later, Antoni and the Krautkammer, they improved the approximation with similar guarantees on the preprocessing and query time. From switch this factor of d became a factor of log s, giving us log squared s over epsilon. And in this paper, what we do is improve the approximation to change one of the log factors to a single log factor, but we lose some polylog s factors. Any questions? These are the main results. I want to spend most of the time telling you about the techniques that led to this result.
Wait, you used or tell us log s or something?
Yes, correct. Yeah. So the tilde, it's log factors of what's inside.
Size of the substance.
Cool. Yeah.
How does this relate to embedding EMD into L1?
Yeah. So we'll see that essentially the first result, it was de facto embedding into L1. The second result, there's a probabilistic guarantee to it, and I'll go exactly to what it is. And then the third result is going to be a data-dependent version of this guarantee. So I want to spend one slide just to convince you that, or give you one kind of nugget of why EMD is a complicated metric to work with. So from a computational perspective, so Pankaj is going to talk about algorithms for tomorrow, you'll see that it's not as simple as computing, say, an L1 or L2. And it's really reflected on this example of Rangel and Tarjan, who showed that really there's this maybe non-locality to EMD that makes it very difficult to reason about. So this is an example where, let's say, blue points are one set, red points are the other. If you're given this instance, then each red point has a very close by blue point at distance 1. However, if you made a mistake and you matched it to the incorrect point, the incorrect side, then because of the matching constraints, there's going to be cascading consequences where you're forced to match things that are further and further away. And if you follow like a simple greedy procedure to build this matching, you're going to get very, very bad approximation, something like polynomial. I think they proved like n to the log of 3/2. Okay, so you really don't want to think of kind of algorithms that make kind of greedy decisions. And this is the whole reason why we look at probabilistic tree embeddings. Okay, so these are going to be the main tool under which we study the Earth mover distance. Okay. So like I said, EMD is not a simple metric. Hopefully I've convinced you all of this. So all the prior approaches to solve, to work in these kind of sketching or nearest neighbor search problems for the Earth mover distance, they all proceed by embedding underlying EMD over RD into a simpler metric. And what that's going to mean for us is to embed the underlying ground metric RD over L1 into a probabilistic tree. Okay? And really the claim is that if you forget about EMD over L1 and you think about EMD over a tree, so imagine the underlying ground metric itself is given by a tree, and now you're trying to match A and B, where A and B are subsets of the leaves. So here A would be, say, the blue points, and B would be the red points. These are the subset of the leaves in some tree. Then there's a very simple, greedy algorithm that optimally produces the matching. Right? The idea is just to like propagate the points up. As the points meet, you match them to each other. And whatever doesn't meet, then you keep propagating up. Your two things met, they get matched to each other. And you kind of keep track of the distance that they've traveled in order to meet at that point, until you've matched everything, and that itself is the optimal matching for that tree. Okay, so this gives us a very kind of straightforward plan toward algorithms. This is the plan that all the previous works have taken, and this is the one that we're going to take. Step one, you generate a probabilistic tree, or an embedding of RD over L1 into this random tree. So here I'm going to write the trees in bold to reflect that these are random variables. So T is a random tree that we sample from, and it measures distances. And once we have a way of taking points in RD and mapping them into the leaves of a tree, we're simply going to think about applying the embedding, which takes each element of your subset, individually applies a tree embedding. So you get now EMD from RDL1 into EMD over that tree that you sampled. This is just the obvious application to each of your S points. And it turns out that, well, the fact that this greedy matching was the optimal one, it's really not super hard to see that once you're here, you're in good shape. You can essentially capture the cost of this bottom-up greedy matching by simple L1 calculation. Okay, any questions so far? Okay, so in the context of probabilistic trees, these are kind of how the results obtain the corresponding nearest neighbor search data structures. So really the work of Indig also builds on this work of, okay, let's see, Charikar, Chakuri, Goel, Guha, Plotkin. I think that's correct, yes. They showed that there's an embedding from RD into a tree, that's the one that we're going to use in order to embed EMD, such that for any two vectors, now these are actually vectors in RD, this distance does not contract, so after you apply the mapping, the distance doesn't shrink. And the expansion is bounded exactly by the approximation factor that we're going to see in the nearest neighbor search data structure. That was the first embedding. Then the second result of Andoni, Indig, and Kraftgammer, now they added this probabilistic guarantee using the fact that the subsets are going to be of size S. So what do they show? They show that there is a probabilistic construction of a tree from RD into a tree, such that if you fix any subset omega of 2S points, think about applying these to the underlying points you're trying to compute. With high probability, the mapping will be non-contracting for all the points in the original ground set omega. And on the other hand, they have bounded expansion with factor log squared s. This is where the log squared s is coming from. Okay, so these were kind of the results that were known. And then what we did a few years ago was essentially switch the quantifiers in this statement and show that by doing so, you could get improved bounds. Okay, so let me just tell you what we did. This was a few years ago with Chen, Jairam, Levy, and myself. We showed that, well, imagine now you don't come up with a distribution. First, fix the subset. Okay, so first fix the subset of points. Now I'm going to produce a tree embedding for that subset. But in addition, this tree embedding is going to be efficiently computable. So if you're familiar with, say, tree embeddings and approximation algorithms, this is never an issue because you get the points and you build the tree for those set of points. But in this setting, we're trying to make sure that we can compute this embedding very quickly because we're going to need it in our data structure. So the theorem says that if you give me a set of points, I can produce a succinct and efficient embedding into a randomized tree such that it also has, it's non-contracting for every point in my universe omega. And now it has improved bounded expansion where it's logarithmic in the size of the set omega. Okay. So this is really what I meant in that this is a data-dependent embedding, because the embedding itself depends on the elements that you're embedding omega. It's still computationally efficient. And if you're only applying it to 2 points, these are 2 subsets of S, omega is size 2s, and we get log S approximation. Okay. Cool. Any questions on the theorem statement?
But you don't know omega because the query is unknown.
Exactly. That's why it's not going to be. It's not going to be enough to just use this theorem. Yeah. Good. But this was kind of our starting point. We looked at this theorem and was like, okay, this is what we had to do. Yeah. Okay. Any other questions?
I think sorry, maybe I'm missing something. So the embedding is of L1, not of
So
ED?
right. So the embedding is an embedding of L1 into a tree, and that gives me a natural way to embed EMD over L1 into EMD over the tree by just applying the element-wise embedding to every single one of my elements in the subset. So my input to EMD is a subset of vectors. I have an embedding that takes vectors, puts them into a tree. Now I apply to each one of those vectors.
Eric, what I'm missing is this, just the FRT will give you these properties, right?
Correct, but it's not neither succinct nor efficient. Yeah, so that's the main point. So in approximation algorithms, you get as input a metric. Linear time in approximation algorithms oftentimes mean like n squared. Okay, here we want to be able to not have to produce the entire metric. Yeah. Yeah.
It seems that you're overdoing in taking omega to be the union of the 2 sets. Would it be hopeful to consider them as pair of S, just a pair of S sets?
Yeah. Yeah.
Because
So
you're keeping inside distances as well, right?
that's correct. So, but in a sense, it's not clear from the definition that the embedding is even defined outside of omega. So we'll see.
No, you mean like you only need like a S by S pairs.
Yeah, exactly.
S cross S only, right? And
Instead of
like,
2 S,
you look at it,
Yeah.
2S choose 2, which is
Yeah.
a bit more. I don't think it's a big difference.
no, it's not a big difference, but maybe you would get,
Sorry, so
maybe
I'm gonna-
it's awful to get something better.
I'm going to think of omega as being like poly S.
Yeah, I understand.
Okay. So I'm not thinking of omega as being the entire metric.
I understand, but still on omega, you want to actually keep the guarantee for any 2 points instead of just the cross product of 2 sets. But okay, maybe it doesn't
Okay,
matter.
yeah. Okay, let me tell you just a little bit about how all of these embeddings work, because it's going to come crucial in our algorithm. Essentially, all these things work by recursively applying shifted grids to them. So essentially, we start with our entire space is RD, and we're just going to recursively subdivide RD, creating a tree. As we start out with the root, as we apply subdivisions, each node corresponds to the region of the space consisting of all the points, and any particular point goes down to a leaf, just where it lies throughout that tree. Okay. So just as an example, when we start with the root, we would apply this. This tells us where to put each point. You apply another division, and so on, until maybe each point is by itself. Okay, good. There's only one change between all of the three embeddings, and that's how you set the corresponding weights to the edges of the tree that you create. So essentially, as we go down this tree at depth I, the side length of the grid is essentially delta over 2 to the I. That's how I'm kind of generating these regions. And the difference between these three works is how they set the weight from going from depth I to depth I plus 1. So essentially, in these first works, they really wanted to get like a true embedding, no probabilistic guarantees, so they really set the weight to be the diameter of the part to make sure that the fact that 2 points got separated, you have sort of enough weights to go from one point to the other point. And this work in AIK, what they did is they say, really, what you should do is you should set the weight such that, well, an expectation, if you multiply that weight times the probability that 2 points were split at that weight, then you would get some unbiased estimator. Now, the challenge is that points sometimes contract, so they needed to pay an extra log factor to overcome a union bound over entire omega. The only change that we did was to say, okay, let's allow the weights to depend on the points that went down that particular tree. So we said, after you sample this tree, in order to compute what the weight is from a node U to a node V, we say sample a point at V, sample a point at U, and the weight is just going to be the average distance of the points that map into those regions. Okay. So let me just say, okay, so we started with this embedding. Why could you or could you not use this probabilistic tree for nearest neighbor search? So the pros is that, well, the dependence on the distortion here, I claimed that this was going to be logarithmic in the size of omega, in the size of the original point set that we're using these weights for. So as long as you keep omega to be poly S, then you're going to get this log S distortion. It's still concise and efficient. The problem is that the embedding itself defines the weights, and these weights are only defined if points from omega went down that part of the tree. In particular, what happens to the query, right? You could have built this tree by looking at your data set. This gives you like the setting for the weights. But really, you're going to have to apply the embedding to some query that you don't know yet. And also, you actually have n subsets of size S. So if you really were to take all of your points, you would have to say omega is size n times s, and then the distortion becomes log n times s, which is much worse. We don't want to do. Okay, so what we're going to do is we're essentially going to try to do what we can, and when we don't have any points, we're just going to use the weights from Andoni and the Krautkammer. So we're going to sample from our data set poly S many points. This is as much as we can support while using the previous embedding, because we have to keep omega to be poly S. These are randomly subset from my data set. And I'm going to build this data-dependent probabilistic tree with respect to that subset omega. And essentially, I'm just going to check if my weights make sense, I'm going to use those weights. So if I'm on a particular node and there's some point that I sampled in my subtree, then I use the weights from CJLW. And if not, well, okay, I just fall back on the weights from Andoni and the Krautkammer. Okay? So in particular, imagine you did have now 2 points, a query and the true nearest neighbor. And imagine somehow that all the points, all the elements of your query and all the elements of your nearest neighbor happen to fall in the points that you sampled in omega. Then you're doing great, because we proved that this had better distortion, log S distortion, you'd be in good shape. The issue is that if your query and your nearest neighbor, if the set that you sampled omega is really far away from all the action, you're essentially just using the guarantees of Andoni, Indyk, and Krautheimer. You will pay a log squared s in the approximation. So really, the theorem that we'd want to prove is something along the following lines that can interpolate, use the better distortion on the sample omega, and degrade gracefully as you get away from omega. So this is maybe the theorem that we'd want to prove. If A and B are 2 points in EMD, and both are close to omega, they're kind of captured by this point set that you sampled omega, then after applying the embedding, you get a log s approximation of the true EMD. Okay, so capture in a way, well, in a neighborhood of omega, you're getting distortion, which is log s. Now, as these points get really far, you will get the log squared s. We really want quantitative bounds on how that happens. And the key question here is, well, what does it mean for a point set A to be close to omega? Now, the natural choice would be to use EMD, right? But EMD is, again, somewhat hard to reason about. So we're going to use it's a relaxation of EMD, or it's known as this chamfer distance. So it's another measure that measures how close a subset of vectors A is to another subset omega. Is known as the chamfer distance, is just the sum of nearest neighbors. Okay, so the chamfer distance between A to omega, this is an asymmetric definition, is the sum of the nearest neighbors for each A in A to the closest X in omega. Okay. Cool. Okay, so let me give you first a naive way to perform the extension that I was talking about. A naive approach, or a weak chamfer extension, would be to say, well, take any A and B. The expected EMD distance in the tree is going to be, well, you're going to pay log squared to move your points in A union B into omega in the tree. But once you move them into omega, you're in the regime where you have better distortion guarantees, so you get an plus log s times EMD. Okay, this is somewhat an intuitive way to think about it. You take the points in AB, you first move them to omega. In the move to omega, you're going from something that you couldn't capture into something that you can capture using the weights of Andoni, Indyk, and Krautheimer. This is what pays the log squared s. But now you're in omega. And in omega, we define the weights such that we got the better distortion. And here we get the stronger guarantees, and this is where this term comes in. Okay, so that would be the weak extension lemma, because it's just naively transferring the points. And oftentimes it could be that remember, n was very big, s was not that big, so poly s is really not capturing that much of the data set. You could be in the situation where the chamfer distance is really just the same as the EMD, so you're effectively paying log squared s. So the main technical claim in the paper is to show that actually this degrades with much better distortion guarantees than this naive bound. It says that for any 2 points A and B, the expected distortion after applying this embedding behaves like a single log s times EMD times inside the log, a measure of how far the points from A were to omega divided by the EMD. Okay? And maybe a very rough proof idea is to just see what is probabilistically happening with this tree and to consider the optimal matching. Imagine A matches B. Okay, so 2 vectors that should get matched to each other. You think of, well, you want to think of transferring A into omega. So C is the closest point to A in omega. And the point is that if A and B are close, when do you pay the weaker weights of AIK? It's the moment that if you had split AB, but you had also split A from C. So in order to kind of pay these weaker guarantees, 2 bad things needed to happen. And it turns out this is enough to get these better distortion guarantees. And I know I'm going a little bit fast because I don't have that much time. But essentially, this gives rise to two cases in our algorithm. Case one, after you sample some set omega, the data set points tend to be far in the sense that the expected chamfer distance for many of the points is, say, bigger than log to the 100s. If such is the case, we actually showed that the previous guarantees of log squared, they should already be good, because here you're in some sense saying that most of the points are really far away from each other, much more than log squared s. So in a way, although you had a weaker distortion guarantees, for this specific data set, it's enough to filter out most of these points. On the other hand, if your points tend to be within log to the 100s, well, then this theorem is basically saying that you pay an extra log s factor. So then we just essentially have an argument that can take the previous locality sensitive hashing, this locality sensitive hashing, and produce one hash function which essentially glues the two cases. OK, I'm running out of time, so let me just finish here. I just have two open problems. The first is that there's nothing ruling out a constant factor approximation. I think you would have to kind of break away from this tree embedding approach. And the second is that sometimes in the literature for ANN, you can get better bounds for Euclidean space than you can for L1. So it's quite possible that even without getting a constant factor approximation, you could use special facts about Euclidean space that allows you to, say, get a square root log s factor approximation. OK, that's all.
Questions for it? You want to start setting up? But sorry, for L2, slightly, yeah. Wouldn't that be better than the embedding itself, like the data-independent embedding?
Sorry, what do you mean?
Like for data-independent embedding, EMD over L1 versus EMD over L2, we have the same bounds, as far as I remember.
That's right. So the question is asking, can you exploit the fact that you're in L2 to get a better guarantee for EMD over L2 than EMD over L1?
Yes. But I mean, it's a question even for data-independent, like standard oblivious embeddings.
Yes. Yes.
Any other questions? If not, let's thank Erik again.